This chip, the DAC 8831, is capable of supplying voltages with near microvolt precision. All you need to do is supply it with the digital code, and it will dial in the voltage for you. And devices, much like this one, are readily available with options for precision, speed, and so on. And that got me thinking, what exactly would it take to make a DAC of your own? Well, as it turns out, it's simultaneously pretty simple and also pretty complicated. The idea is easy enough, but the challenge lies in the execution. In case we aren't on the same page, DAC is an acronym for Digital to Analog Converter. Basically, it takes some sort of digital number and converts it into an analog voltage. The digital number you give it serves as a sort of fraction. More specifically, fractional output between a known voltage, which we can call Vref, and 0. The more bits that you have, the more resolution, since there are more possible output states that you can specify. This number that we give the DAC is called the DAC code. There are several different architectures that you can use to achieve this functionality. For example, R2R DACs use a pattern of resistors in a ladder shape to add or remove voltage to the output depending on the inputs. A delta sigma DAC uses a low-bit DAC in filtering to achieve precise analog outputs. There are quite a few more DACs, but there is one in particular that I'd like to focus on today. Let me introduce to you a string DAC with interpolation. Okay, before we talk about the interpolation part, let's make sure that you understand what a string DAC is. A string DAC is probably the simplest DAC that there is. Let's take a look at a resistor divider with just 2 resistors having equal values, and with 2 switches. And congratulations, you've just made a 1-bit string DAC. As you might know, a resistor divider does what the name implies. It divides between the 2 voltages. Our 2 switches allow our bit to select which voltage we want. For example, if the bit is 0, we select the lower switch and get 0 volts on the output. But if the bit is a 1, we select the upper switch and get half of Vref. Okay, easy enough. But what about a 2-bit string DAC? Well, you just build a resistor divider with more resistors and more switches. As you can see, we are still selecting a voltage between 0 and Vref, but this time we are given much more resolution. Now we can select 0, quarter of Vref, half of Vref, and 3/4 of Vref. If Vref was 1 volt, that would correspond to 0, 0.25, 0.5, and 0.75 volts respectively. And with a 3-bit DAC? Well, we just continue the pattern with 8 resistors and switches. Hopefully now you can see the pattern that each additional bit doubles the number of switches and resistors that we need. You can express this mathematically as 2 to the power of n, where n is the number of bits. If you wanted, say, a 16-bit DAC, then you would need 65,000 switches and resistors. So clearly, you want to avoid using this many bits with a single string DAC. Luckily, there's a way that you can divide up the DAC into multiple parts. That way, we can avoid the danger of those large exponential numbers. Let's turn this 4-bit string into 2 2-bit strings. On the first 2-bit string, instead of tapping into only one of the outputs, let's tap into 2 of the outputs. Let's name these 2 outputs V-low and V-high. We will also have to add an additional switch at the top to allow for a pair to be formed at the highest input. And as you can see, we can still move the output through the string, but this time we have 2 outputs. The difference between V-low and V-high is always the same in an ideal DAC. For example, if Vref is 4 volts, then the difference between V-low and V-high will always be 1 volt, no matter where they are placed in the string. Here comes the interesting part. We can further divide up the difference between V-low and V-high by placing them at the top and bottom of our secondary DAC. In order to prevent loading of the main string, we place these analog voltage buffers. Now, we can further divide between V-low and V-high. And with this, we have reduced the component count from 16 resistors and switches down to just 9. If we were to do this with a 16-bit DAC, but divide it up into 2 8-bit DACs, then we'd reduce the component count from 65,536 down to just 513 plus 2 buffers, which is a massive improvement. Let's design a string of our own. To keep the experiment somewhat manageable for myself, I made a 6-bit string DAC. This was mostly because a larger number of bits would have made the string much too long. Anyway, A 6-bit string DAC with a dual output needs 64 resistors and 65 switches. For the resistors, I chose 0.5% 1K ohm resistors in a 0603 package. These resistors were cheap, coming in at about 2 cents each. The 0603 package allowed me to save space on the PCB, and the 0.5% tolerance allowed for a little bit better accuracy. Now, for the switches. I wanted to use discrete Mosfets at first, since they would make for good analog switches. But I quickly remembered that discrete Mosfets don't come with a connection to the substrate. Instead, it is connected to the source internally, which creates this body diode you always see on the diagrams. This diode is undesirable to our situation. To fix the problem, you could put 2 transistors back to back in order to null out the effect of the diodes. This creates a new problem though, in that it doubles the number of transistors that would be needed. I did end up using this method for the high switch, but for all the others I found a different solution. The 74HC4051 is an analog multiplexer. It functions in a similar way as our switches from earlier, but it also comes in a more compact package, and it has internal decoding logic. Since it is an 8-to-1 multiplexer, it will use 3 of our 6 bits. This also means that we will need 8 of them to stand in for all 64 of our switches. You may be wondering now, if we are using 3 bits of the multiplexer now, how will we use the other 3 to select the correct multiplexer and switch? Well, before we do that, I want to revisit our V-low and V-high outputs again. Before, I simply marked the outputs as either V-low or V-high. But how would we route them to the correct place? We could use 2 sets of switches on each node and either connect it to V-low or V-high. But as you can probably tell, that's pretty inefficient. Instead, we can combine and divide the string outputs into 2 separate lines, which I termed bus 1 and bus 2. At any time, only one switch will power the bus at a time. And we can use some logic and switching later on to decide which bus is connected to V-low and which bus is connected to V-high. In fact, when using this system, each bus will alternate between being V-low and V-high. And increasing the input code will only toggle one switch at a time, which means each bus will take turns incrementing their count. This reduces switching disturbances on the output, and even better, it greatly reduces circuit component count. You will, however, have to spend some time figuring out how exactly you should decode the main input to each of these buses. And after some time brainstorming in my notebook, I found the solution. You'll notice that since we divided the switches up into 2 separate groups, we need 1 fewer bit for the switch codes. This is easily done for both groups by simply dividing the main code by 2. And since we are using binary, a division by 2 is done with a singular bit shift to the right. You can do this in the schematic by remapping the bits to skip over bit 0. But we aren't quite done yet. Earlier, I mentioned how the buses should take turns incrementing. Well, we can use the remainder of the division that we just completed. Simply add the remainder of the division to bus 1. We can find the remainder in bit 0, which we initially threw away. This way, when the code is even, both buses have the same input. But when it is odd, bus 1 is a single code ahead. In this manner, bus 2 will always be catching up to bus 1, creating this alternating pattern. This addition of 1 does mean that we will have to reintroduce a 6th bit into the bus 1 code, but that doesn't matter too much. And finally, we can decide whether bus 1 and bus 2 are either V-low or V-high by using bit 0 again. When bit 0 is low, then bus 1 is V-low and bus 2 is V-high, and vice versa for when bit 0 is high. Now, let's implement this all into the schematic. Like I mentioned, the division by 2 is rather easy. Simply exclude bit 0 and bit shift everything to the right. The addition is a bit more complicated, since we will need to use a full adder IC. Luckily, the CD74HCT283 does the job rather well. I needed to use 2 of them since each one only adds 4 bits individually. Connecting the carry output and input allows you to cascade the adders together, giving us 8 bits of adding in total. Now that we have the input codes for each of the buses, we just need to decode them into selecting the correct switch that we need. Like I mentioned earlier, the multiplexers already decode the first 3 bits for us. We just need to take care of the rest of the bits ourselves. The multiplexers have an enable input, which allows us to turn off all of the switches if it's high. So I used a group of inverters and an AND gate for each multiplexer. Now, the multiplexer is only active if bit 3 and 4 are the correct value. The high switch is easy, since it's only active if bit 5 on bus 1 is active. The last couple of things that I added to the schematic were this binary buffer with pull-down resistors. This way, I didn't have to worry about floating inputs. I also added a VREF for a string. It was the ref 5020. This is a precise voltage reference that will output a constant 2.048 volts. And of course, I added many decoupling capacitors. The PCB layout wasn't the craziest thing. It was just a really long board because of the resistor string. And other than the string, I placed all of the bus 2 multiplexers on the bottom of the board so as not to clutter things up. All that was left to do was generate the Gerber files and have the boards manufactured. And luckily, today's sponsor is perfect for this. JLC PCB is a really great choice for any PCB project. And in addition to PCB manufacturing, they provide PCB assembly, SMT standstills, 3D printing, CNC machining, and mechatronic parts. This makes JLC PCB not only a very convenient service, but also very fast and affordable for any electronics project. I've been using JLC PCB for quite a while now, and their quick manufacturing time, along with high quality PCBs, has made my life so much easier. It's super easy to have JLC PCB make your board. Just drag and drop your Gerber files, and JLC PCB will give you a quote. Once I ordered and received the boards, they were very high quality. I was especially impressed by the 6-layer board that I received, and that they were able to manufacture the string DAC board despite it being quite long. The stencils were also phenomenal as well. If you've been unsure of where to get your PCBs manufactured, definitely visit JLC PCB. They have a $30 coupon for 6-layer boards right now, which means you can get a 6-layer board starting at just $5. Thank you JLC PCB for sponsoring this video, and let's put this board together. I'll put the 6-layer board aside for now, since I will explain its purpose a bit later in the video. To assemble the string DAC, I held it in place with the duplicate PCBs and taped them down. I then aligned the stencil and taped that down as well. Afterwards, I applied a bunch of this solder paste and spread it all out with a gift card. Afterwards, I removed the stencil and started placing down all the components. Once that was done, I placed the board on a hot plate. For these larger boards, I recommend holding them down at the corners to ensure even heat spreading. Unfortunately, I can only use the hot plate method for the top of the board. For the bottom, I had to hand solder it all together. Having this microscope helps a lot with the SMD hand soldering, but it's also definitely doable without one. Just make sure that you aren't accidentally shorting pins together, especially on these really finely spaced pins. To clean off the board, I recommend using some sort of alcohol. I used 99% isopropyl alcohol. You can use a brush to clean everything off, but luckily I got this cool new toy to play with. Introducing the ultrasonic bath. It works by passing high-frequency sound waves through the bath, creating tiny bubbles which then collapse and remove contaminants from the PCB. It took 3 quarts of isopropyl alcohol to fill the bath, which is quite a bit. I then placed my PCBs and my tweezers in the bath for cleaning. I set the temperature to 105 Fahrenheit and let it clean for 10 minutes. Make sure to put the lid on so that the alcohol stays in the bath, since it evaporates pretty quickly. After it was done, I made sure to drain all of the alcohol from the bath into a separate container. This stuff isn't the cheapest, so I think it's a good idea to reuse it for future baths. I was really impressed by how clean the items were after the bath though. All of the sticky residue from the flux was completely removed. And since it was isopropyl, the boards dried very quickly. Now we can finally test the string DAC, except not quite yet since there were a few errors. I had to go back and find a bunch of these tiny issues with my hot plate soldering, which is weird since hot plate soldering is usually the easy part. Nothing wrong with JLC PCB services, I think I just went a bit light on the solder paste in a few spots. After resoldering loose joints and disconnecting a couple of shorter joints, the board worked. Well, almost. Somehow, I overlooked what happens when the highest switch on bus 1 is activated in the DAC. You see, when bit 5 is active, so is the switch, which is correct. But the part that I overlooked is that the lowest multiplexer doesn't take this into account and just sees the 0 code. This means that the highest and lowest switches are active simultaneously when we are at the full scale code for bus 1. Luckily, it was a somewhat easy fix. I found this MM74HC32N OR gate IC in my parts bin. To get it to fit on my board, I bent all the pins up. Since I was only going to use one of the OR gates, I clipped all of the other outputs. And luckily for me, I placed a ground test point in a convenient spot. So I was able to use that as an anchor point for the chip. I then cut the trace between the inverter and the enable pin of the multiplexer. Basically, I want the multiplexer to function in the same way as before, but also disable when bit 5 is active. The OR gate allows this since a high signal disables the multiplexer. I wired up the connections with copper wire, and that solved the problem. Now we just need a way to test all of the input codes. You could do this manually, but I think I'd rather computerize the whole process. Before we test our DIY DAC, I'd like to first test a commercial DAC chip so we have a point of reference to compare it to. For this, I'll be using the DAC 8831, which I mentioned in the intro. I will be creating a testing platform which will have a DAC code writer, the DAC itself, a voltage reference, and a measurement device, all controlled by a PC. And when I mention a PC, I really mean a Raspberry Pi, since I'd rather not dedicate my main computer to this test. For the code writer, I opted to go with an Atmega 8A, which is my go-to microcontroller for easy experimentation. My idea is that the PC will send a command over serial. The Atmega 8A will then decode that command and send it to the DAC itself. To allow control over serial, I added an FTDI board to convert from USB to serial. The Atmega 8A then connects to the DAC using SCPI. When writing code for the Atmega, I was able to copy the basics from other projects that I've made in the past. We need to be able to receive characters from the UART and to send 16-bit data to the DAC. Sending 16-bit data was easy enough. Simply do 2 SPI writes and keep CS low until both bytes have been written. Receiving characters over UART was easy enough, since I've already written code for that in the past. The hard part was receiving multiple characters and putting them all together into a single string. To do that, I made a loop that would fill up a buffer until it was either full or a new line character was detected. We are able to tell if the buffer overflowed when nulls returned from the function. I then made a base of a kind of overkill command decoding system. Basically, it decodes a command in the form of code, base, and value. Either way, I was able to get it working. I wrote a Python script on the PC side that sends the command over serial, allowing me to select any arbitrary code from my command line. But what good is being able to automate setting the code if we can't automate reading it either? Well, that's where this multimeter comes in. This is a Keithley 2010 7.5 digit meter, which makes it plenty accurate enough to read the precise voltage output of the DAC. And it comes with a serial port on the back of it as well, allowing for remote reading and control. The serial interface then uses the SCPI protocol for sending commands. Luckily, SCPI isn't all that difficult to understand. The basic structure of an SCPI command is as follows. The command you'd like to execute potentially followed by the value for that argument and ended with a new line. Well, it isn't always a new line, but that's the way I set it up. Make sure to change your meter settings to terminate with a new line if you ever decide to follow along. The commands themselves also have an interesting structure. They name themselves in a sort of hierarchy pattern, with each level separated by a colon. For example, to set the number of digits the multimeter reads, we first need to specify that we are measuring a voltage, and then further specify that we are measuring a DC voltage. Then we'd finally tell it how many digits we'd like to use. The format also looks really odd since the capitalization seems kind of inconsistent. There is a reason for this though, and that is that the lowercase letters are actually optional, since the uppercase letters are enough for the meter to deduce which command you are talking about. I left in all of the lowercase letters just to make it a bit easier for us to read. A good way to test whether your system works is by sending the identification command. If it was successful, the meter sends back information about itself. After you successfully identify the meter, you should then configure it. The first thing to do is set it to measure DC voltage by using the function command. I then set it to measure 10 power line cycles. A PLC, like I just said, stands for power line cycle, and it represents the amount of time that it takes for the AC mains input to complete one period. So, 10 PLCs means that it takes the meter 10 power line cycles to complete one reading. A longer integration time allows for more accurate readings, but it also makes the test take a bit longer. I also disabled auto ranging in order to ensure that any gain error remained consistent throughout the test. And of course, all 7.5 digits of the meter were used. The filter averages multiple readings together to get one average reading. I disabled it for this test though. And finally, I enabled auto zero. To read from the meter, you send the read command and receive the data over serial. With the SCPI protocol figured out, we are now able to script an all codes test. Basically, we want to determine the voltage output at every single input code. It's really simple. All we have to do is run a for loop with 65,536 iterations. Inside of the loop, we write the DAC code, wait a second for the output to settle, and then read the voltage from the meter. Once the loop is complete, we save all of those readings into a CSV file. Now, all that's left is just to run the code. I can finally explain to you why we'd want to know the output value of each code. The first is that we want to make sure that every code is close to what it ideally be. For example, hex 8000, which is half of the full-scale code, should output exactly half of the reference voltage. A graph that would display this would be an INL chart. INL stands for integral nonlinearity, and it shows us just how much the output differs from the ideal. For example, an ideal DAC would have a perfectly straight output line, and the INL chart would have an ideal value of 0. A less ideal DAC might have an output like this, where the middle codes are a great deal larger than they should be. And as you can see, the INL chart makes it much easier to visualize how much it deviates from the ideal. Now, let's take a look at our DAC 8831. As you can see, just by looking at the output versus the input code, it looks like an ideal DAC, aside from the beginning bit. This is where the INL chart really shines, since we can more easily zoom in on the error. And my first attempt at the chart didn't really go that well, and it had something to do with my measurement. I think that the problem is that since the DAC 8831 is an unbuffered DAC, my multimeter's internal resistance was messing with the R2R structure at first. But the good news is that this problem disappears at higher codes. So I adjusted the chart to consider the INL from code 6000 to full scale. As you can see, the output range stays very close to what it should be, staying within about -1.5 LSBs. In case you didn't know, when I refer to an LSB, I mean the amount of voltage that increasing the code by 1 should give us. So 1 LSB is equal to 31.2 microvolts in our case. In other words, the DAC output stays within about 40 microvolts of what we should predict from an ideal DAC. Compared to the datasheet, our INL chart is pretty good. The differences could be attributed to my test setup, or just differences in the device under test. There is another kind of nonlinearity that we should take a look at, DNL. DNL stands for differential nonlinearity. DNL is different from INL since it doesn't keep track of the overall output, but rather the difference between two adjacent codes. For example, if we start at code 7000 and then increment it to code 7001, the DNL at that code would be the voltage difference between them minus 1 LSB. Again, we adjust the voltage into our LSB unit, and an ideal DNL chart would stay at 0 for every code. This means that every code should increase by exactly 1 LSB in an ideal DAC. If, for example, the code increased by 1.5 LSB, then we would have an error of 0.5 LSB, since it is 0.5 higher than the ideal 1 LSB target. If we take a look at the DNL chart of the DAC 8831, we will find great performance with the error generally staying underneath plus minus 0.25 LSBs. This data actually lines up really well with the datasheets. This chart is actually really important for a very specific reason. You really don't want the DNL to ever go below -1. Why is this so important? Well, if the DNL goes below -1, then that means that increasing the DAC code actually causes the output voltage to decrease. This can be a big problem for control systems. The ability to not do this, in other words, to always stay above -1 DNL, is called monotonicity. And since the DAC 8831 never comes close to dipping below -1 DNL, we can call it a monotonic DAC. This is one of the advantages of a string DAC actually, since it is literally impossible for a higher code to give you a lower voltage. That is unless you somehow have a negative resistance. But if that's the case, then you'd probably have bigger ideas than the monotonicity of a string DAC. With that out of the way, let me show you how the DIY string DAC performed. Each graph I'll show you will come in a pair, since we have a V low and a V high output. I did this to make sure that the behavior of each output is consistent with the other. Also remember that we are only dealing with 6 bits right now, so in this case, each LSB is 32 millivolts. That's why the data seems so impressive, because it's really easy to hit a 32 millivolt target compared to something like a 32 microvolt target that we were looking at before. And while the string DAC makes some interesting shapes, it really isn't the reason why I made this video. Let's finally talk about what I meant when I said the DAC in this video was made as a string DAC with interpolation. Like I mentioned earlier, you can split up your string DAC into 2 pieces, and this greatly reduces the number of resistors and switches. But it comes at the cost of needing 2 additional buffers. The circuit that I'm about to show you not only eliminates the string buffers, but can also partially eliminate an output buffer. And it has the same output behavior as the second string. To begin, let me show you an op-amp buffer. It's a lot like the op-amp that I've shown you in a previous video. I'd recommend watching that if you don't know what I mean when I say differential pair. I've gone ahead and changed this design to use Mosfets because they have much higher input impedance compared to BJTs, which is the thing that will allow us to eliminate the string buffers. Anyways, as you should know from the op-amp video, when we wire the inverting input to the output, we buffer the output. In other words, the voltage on the non-inverting input is buffered onto the output. Let's permanently keep this first input connected to VLO. The thing I'm about to show you now is a bit unconventional, and it's where the magic of the circuit lies. Let's parallel another differential pair to the first. This is going to look really odd the first time that you see it, but at its core, it's still our op-amp buffer from before, just with 2 different inputs this time. If we connect this new input to VLO, then really nothing changes since our output will still drive VLO on the output. But what if we connect it to V high? Well, this is where things get interesting. The first differential pair wants the output to be V low, and the second pair wants it to be V high. They will both split their currents according to what the goal of the pair is. This splitting of currents causes the outputs to be exactly equal to half of V low and V high. You may now notice that this is a 1-bit DAC. Placing a 0, or in this case V low, on the input gives us V low as a whole. Placing a 1, or in this case V high, we get half of the difference between V low and V high. And since we are using Mosfets, V low and V high aren't loaded from the gate impedance. Now, how would we create a 2-bit DAC from this? Well, a 2-bit DAC has 4 possible output states. So we need to distribute the current in 4 possible ways. This means that we need 4 differential pairs. Again, the very first pair is always V low. The second pair is bit 0, and the third and fourth pairs together are both bit 1. At code 0, all pairs are V low, so we get V low. At full scale, 3 of the 4 pairs are V high, so we get 3/4 of V high. And at mid scale, 2 of them are V high, and the other 2 are V low, so we get half the voltage on the output. At this point, you should be able to notice that this is the same behavior that we had when we were examining the 2-bit DAC at the beginning of the video. You will also notice that we run into the same exponential problem. But this is okay, since we are reducing the number of bits anyway by cascading DACs, but we can still improve on it. Instead of using 2 differential pairs with the same current for the second bit, we can use 1 differential pair with double the current. So, instead of using an exponential number for differential pairs, we are using an increasing current. This is a really nice trick to save space. But it does degrade linearity performance since the pairs are no longer identical. I found in my simulations that a good balance between maintaining identical pairs and saving space is having at most 4 times the current of the first differential pair. This approximately reduces the number of pairs that we need by 4, which is great since we are going to be making this interpolator 8 bits long. Before we build up all of those differential pairs though, let's make a few improvements to the core op-amp first. The lower current mirror can easily be improved by giving it a cascode. This helps because changing the drain source voltage on the FETs changes the drain current a bit, and the cascode keeps that voltage more constant. This now causes another problem, where we can't go nearly as low as the output voltage wants us to be. A few other iterations of this design had the same problem, so I decided to shift the whole headroom problem up to the positive rail since we have plenty of voltage up there. To do that, I added a folded cascode. You may be familiar with cascodes from my BJT video. and a folded cascode has the same properties as a normal cascode, with the exception that we use different polarity transistors. And in this case, we go from the p-channel differential pair to the n-channel cascode transistors. We do need an additional current source for each of the cascodes though. The bias voltage for the cascode is generated by a green LED, which gives us roughly 3 volts. We top off the cascode with a current mirror in the same way that you would with a traditional op-amp. The output stage is also the same with a Class B configuration, which means that we no longer need a dedicated output power buffer. Let's now talk about how we will translate those 1s and 0s into V high and V low inputs. And it's actually really simple. Remember that analog switch we talked about back in the string DAC section of this video? Well, we can actually do that to either switch V low or V high to each of the differential pair groups depending on the value of the corresponding bit. All we need is a few of those Mosfets and a few logic inverters. This whole design works really well in the simulator, but it most definitely won't work like this in real life. Remember how I said that linearity is affected by how identical each pair is? Well, in real life, we have to worry about the matching of each Mosfet in each pair. This isn't that much of a problem for integrated DACs, since they are all manufactured on the same silicon, using the same process, which means that the matching errors will be minimal. But we will be making this out of discrete transistors, so we won't have that advantage. Let's see how easily we can match each Mosfet by hand. I have a pair of these 2N7000 N-channel Mosfets that we can compare. If you have one of these semiconductor analyzer tools, it's really easy to test actually. Simply connect a lead to each Mosfet pin. It doesn't matter which order you place the pins, since the tool will figure out which pin it is for itself. Click Test and you will get back all that you would ever need to know about this Mosfet. But what if you don't have one of these analyzers? Well, let's take a look at some manual testing. Mosfets operate on a principle called transconductance, which basically means that a voltage on the gate will cause a current to flow through the drain. For our testing circuit, I will place a Mosfet in series with a 1K resistor. Our supply voltage will be 10 volts. The idea here is that we will place specific voltages on the Mosfet's gate, and we will measure the current through the Mosfet's drain. So I started the test by incrementing the voltage in roughly 100 millivolt steps. A handheld multimeter was used to verify the gate voltage, and the bench multimeter was used to measure the current. As expected, increasing the gate voltage increased the drain current. What's interesting to note though is that the relationship between the two is exponential. Up to a certain point, increasing the gate voltage doesn't affect the current very much. In this state, we can say that the Mosfet is off. But at the threshold voltage, it suddenly increases very quickly. The DCA tool defines the threshold voltage at the point where the drain current is equal to 5 milliamps. So the equivalent here would be about 1.8 volts. My data gets capped at about 10 milliamps because of the 1K resistor. If I were to remove it, then we would get much larger currents. The datasheet actually has a plot for this data themselves, and the results line up closely enough. It also shows us just how much current you can get through the device with enough of a gate voltage. I'd also like to point your attention to the threshold voltage figure on the datasheet. You'll see that the difference between the minimum, typical, and maximum values has a huge range. That's a 2.2 voltage difference between minimum and maximum. This is a rather big problem for us when we are trying to make a precise analog circuit, since I'd rather not have to go through and match hundreds of Mosfets into pairs. To get a better feel for this, let's make 2 current mirrors from random Mosfets to function as current sources and see how well they are matched. I'm aiming for about 25 milliamps through each current mirror, so I set up the Mosfet with a 100 ohm resistor. The other 2 should ideally be 25 milliamps as well, since they all share the same gate voltage. But here on the breadboard, the matching just isn't there. The main FET has 27 milliamps flowing through it, the first mirror has 23.7 milliamps, and the second mirror has 29.2 milliamps. So, as you can see, it's using Mosfets alone that causes too massive a difference to be used reliably alone like this, unless you want to match them all by hand. If you have watched my video on bipolar transistors, then you should be familiar with emitter degeneration. Mosfets have a similar setup in the form of source degeneration. The larger the source resistor, the less the transconductance value of the Mosfet affects the transconductance value of the circuit as a whole. I tried out several different source resistors on our current mirror, and the current values did start to converge. At just 22 ohms, they were 11.25 milliamps and 9.71 milliamps respectively. At 220 ohms, they were 1.93 milliamps and 2.1 milliamps. And at 2.2 k ohms, they were 641 microamps and 293 microamps. This is definitely interesting because it demonstrates how increasing source degeneration greatly improves matching, but it comes at the cost of greatly reducing your gain. This shouldn't be an issue though, since we are aiming for an identical but constant current from these devices. To get even better results, we should also degenerate our reference transistor. But at this point, I think it's safe to say that we've outgrown the breadboard. To get a proper demonstration of how well this degeneration improves matching, I got 3 of the Mosfets that I will use in the final design, which were these small SMD types. I put all 3 of them on these adapter boards and put them on the circuit together on the prototyping board. This time, all of the transistors have 56 ohm degeneration resistors. The currents this time were 19 milliamps for the reference current, and 18.6 milliamps for the first mirror, and 18.89 milliamps for the second mirror. This is much better compared to before, but the currents are still somewhat off from each other. To combat this in the final design, I decided to add trim pots to all the currents that needed to be precise. At this point, I also got to wondering whether source degeneration would help with the differential pairs, and not just the current sources. Yes, the source degeneration kills our gain, but that's okay since we don't really need much gain anyways. It does essentially eliminate the differences in transconductance between each Mosfet. The simulation still works well even with all these source degenerators, so I decided to go ahead and apply this to my schematic with the hope that I wouldn't have to manually match each of these pairs. Anyways, with the schematic complete, I went ahead and completed the layout using 6 layers. Thanks again to JLC-PCB for supplying these boards. They did a great job with both of them. The SMD soldering for this one was much easier than the string, since the vast majority of the components were on the top layer of the board this time around. I was able to use a hot plate to solder everything on the top, and then I hand soldered the resistors and the capacitors on the back. The hard part for this board was soldering all of those 1x2 headers. Once I was done soldering, this board got a bath just like the other board did. The purpose of the headers was to allow me to calibrate the current sources by measuring them with my multimeter. Once the current was at its appropriate value, I connected it to the circuit with a jumper. This also took a while to get all the current sources at the correct values. But once I was done, I verified that the circuit was working by double checking that the output was buffering V low when all the inputs were 0. There was a bit of a DC offset on the output, but I figured that it could be trimmed later if needed. Let's get into those linearity measurements. I hooked up the string DACs V low and V high to the V low and V high inputs on the Interpolator circuit. The first thing that I did was set up a constant full scale on the string. I then set my tester to run through all 8 bits of our interpolator. And, well, here's the result. We get this repeating spiky pattern, which unfortunately means that this DAC is not monotonic. But why is it like this? Well, remember our discussion on the matching of the differential pairs? Well, it occurred to me that after putting this together, that while the degeneration solved many of the problems with the matching transconductance values, it did not completely solve the problems with matching the gate threshold voltages. You'll also see that the pattern occurs pretty often. This means that the lower bits of the DAC are contributing the most to it. The upper bits also have problems matching with each other, but they also have multiple pairs per bit, which means that the matching error gets averaged out. The performance of the DAC is still somewhat encouraging for a DIY attempt. According to the INL chart, we are always within about plus minus 3 lsb everywhere on the interpolator. In this case, since the DAC overall is 14 bits, 1 LSB should be 125 microvolts, which makes 3 LSBs equal to 375 microvolts. So we can at least say that we have sub-millivolt precision. With all the interpolators testing complete, let's test the DAC as a whole now. Just as a reminder, this is a 14-bit DAC, so that means we will have 16,384 steps to go through. After a couple of hours, the test was complete. The DNL plot is what we would expect from the previous DNL plot of the interpolator, with a maximum of about 2 LSBs and a typical minimum of about negative 3.5 LSBs. The INL plot was rather disappointing though, with a peak of 130 LSBs, which is equal to 16 millivolts. Either way, this is a good demonstration of why these plots are so important, since the output voltage doesn't really show us the behavior on its own. For the entirety of this video, you may have been wondering why I was even bothering with this whole interpolator system when we could have just used a secondary string. Well, like I mentioned earlier, it removes the need for all of those resistors, switches, those two buffers, and potentially the output buffer as well. This sounds ridiculous when you look at the size of my board, but this is really just an educational demonstration for YouTube. In reality, this method only saves space if you are working on a semiconductor, where everything is much, much smaller. Remember, there are no monolithic buffer ICs or multiplexers in nice, neat packages on the semiconductor scale. Instead, each transistor must be drawn at a similar scale to all of the others. If we go by transistor count, my design still used fewer transistors than if I had gone with an equivalent dual string. The string DAC used 65 switches, which we will approximate to 65 transistors. There were 6 switches to direct bus 1 and bus 2 to V low and V high. The interpolator used 245 transistors. Combined, my project overall had an approximate 316 transistors, not counting the string DAC's digital decoding logic. A similar 14-bit DAC made from a 6-bit DAC cascaded by an 8-bit string DAC would use 321 transistors on switches alone. This doesn't account for the additional decoding logic needed for the second string, nor does it account for the additional buffers, nor does it account for the additional 256 resistors. Hopefully you can now see why I've shown you this circuit, and why it's important for DACs designed on a semiconductor. This design is great for saving space on a chip surface, but it isn't really that practical for discrete designs, and you would probably get better performance by just using a second string. Well, that's kind of it for this DAC. While we weren't able to completely match the specifications of commercial DACs that you might find online, I think we made some great progress in understanding how these devices work. Anyway, if you've enjoyed this video and learned something new, please consider subscribing so that you can see my future videos. Also, visit my Buy Me a Coffee page, because with your support I can keep making these videos. I'd like to take a moment to thank Mr. Deb Knoll, Cognizant, and Mark for being channel members. You all have made this video possible. Anyways, thanks for watching. Have a good one.